Good evening, everyone. My name is Andrew Fracknoy. I'm the astronomy instructor here at Foothill College, and it's my pleasure to welcome everyone in the auditorium and all those of you listening or watching on the web to the first 2009 Silicon Valley Astronomy Lecture Series. This is a program sponsored by NASA's Ames Research Center, the Foothill College Astronomy Program, the Astronomical Society of the Pacific, and the SETI Institute to bring new ideas and new discoveries in astronomy to a wider public. This evening, we're very pleased to welcome a speaker who's going to talk to us about crashing on the moon on purpose. Our speaker is Dr. Anthony Colaprete, a planetary scientist at NASA Ames, and the principal investigator for the LCROSS mission. He received both his undergraduate and graduate degrees from the University of Colorado and worked on a number of sounding rocket, space shuttle, and small satellite projects before graduating to crashing the moon, because that's what LCROSS is going to do. His research specialties include the climates and clouds of other planets, particularly Mars, and impacts and the clouds of dust they generate. And you'll see how important impacts will be in the discussion of the mission that he is the scientific leader of. At Ames, he's also the leader in the development of future instruments for exploring Mars and the moon. So, ladies and gentlemen, here to tell us about this unique experiment of crashing into the moon on purpose, it's my pleasure to introduce Dr. Anthony Colaprete.
Thank you. It's great to be here tonight. I am a first-time visitor, but hopefully that'll change. This looks like a really great series, and just by the show of repeats, it says a lot about how great it really is. I will try to stay near the podium, I've been told, but I do tend to wander a bit, so we'll see how this goes. I'm also going to turn off my wireless to save my battery here. It'd be a shame if we quit halfway through. I'm the principal investigator for LCROSS, as was mentioned. I'm also the payload manager, which we can get into later, but I frequently had fights with myself. We want more science, you can't afford it. We want more, can't afford it. But as you'll see in a minute, LCROSS is actually a very unique mission in a lot of ways. It's a unique scientific mission, but it's also a unique mission for NASA. It represents a different flavor of mission than NASA typically does. And you'll see how that is a little bit later in the presentation. Tonight I want to talk about first what LCROSS is about. What is it trying to do? What's its motivation? Why are we doing it? A little bit about the expectations, what we'll learn, that sort of thing, and then jump into the actual project itself. LCROSS was really motivated about 10 years ago by another NASA Ames mission called Lunar Prospector. Lunar Prospector was another low-cost mission. It was one of the very first, if not the first, Discovery class missions that NASA flew. It was so simple it didn't even have a computer on board. But it studied the moon, and in particular, it had an instrument that studied neutrons. These neutrons emitted from the soil of the moon are absorbed by a variety of elements, including hydrogen. Now, one of the things that it discovered was hydrogen was in abundance, in excess, near the poles of the moon. And I have this little figure here from Bill Farrell's original paper. What this just shows is the amount of neutrons measured. Where it's bright, there's more neutrons. Where it's dark, there's fewer neutrons. And so what that means, so you interpret that as, there is less hydrogen here and more hydrogen here. It was interesting that the hydrogen was in excess at the poles. People immediately thought, well, what's unique about the poles on the moon? Oh, it might be colder there. So maybe there's some volatility related to the increase of these hydrogen atoms at the poles of the moon. Now that was the thing. The instrument on Lunar Prospector could only measure hydrogen. It couldn't tell you what form it was in. So we don't know that it's water. So that's one of the principal questions that's remained ever since and been heavily debated since Lunar Prospector discovered this 10 years ago is, what is the form of that hydrogen? So that's what LCROSS is really all about. It's trying to understand what is the form of this hydrogen, what's its distribution, and where is it located. So that's kind of what I've written out here is the debate over the form and concentration of this hydrogen has really been raging, and I'll get into this later. Some extreme camps have been established. It's this way, and that's usually the case when there's very little data. This is about all the data we have right now. So LCROSS and future missions will really add to this. So adding to this then, got some kind of motherhood statements that you usually see in a project presentation, and I had to include them here. So this is an LCROSS mission rationale listed out here. It's what I just said. We want to understand what this hydrogen is. We want to know its quantity, form, and distribution. We want to use these measurements as ground truths for the other measurements that will be made by the Lunar Reconnaissance Orbiter. LRO, Lunar Reconnaissance Orbiter, is the spacecraft we're hitching a ride with to the moon. It has a neutron measuring instrument on it as well that will make better measurements. We want to provide a ground truth, meaning we'll sample the dirt you're measuring, and so then you can tie the two measurements together, kind of calibrate your measurements. One of the interesting parts about LCROSS, and LRO for that matter, is these are ESMD missions. And what does ESMD mean? This is a particular division within NASA. There's the Science Mission Directorate. This is the Exploration Systems Missions Directorate. The Exploration Systems is the directorate or the division within NASA that's building the Ares rocket, the Orion capsule. They're the directorate that's responsible for bringing humans back to the moon. So they are the ones who are sponsoring these missions as exploration tools, the robotic precursors to understand what it is, where we're going, and where we need to go and consider. LROs, you'll see later, will map the moon at unprecedented detail, providing the kind of information to do highly precise landings on the moon and more hazardous places than we went to with Apollo. LCROSS actually provides a bit of information that will be decisive. We're very interested in the poles for a lot of reasons. One of the reasons is water. It could be a valuable resource. So moving on past this then, there are a lot of science mission objectives associated with this mission as well. So we have the support of the Science Mission Directorate within NASA, and we're working very closely with them. And I've listed some of the basic questions here. Fundamentally, we're going someplace we've never been before. We've never been to the poles of the moon. We've always, all the other our landers on the moon have landed near the equator in the tropics. We've never been to the poles with a lander. We've never explored inside one of these craters that has never seen the light of day. The floor of some of these craters have not seen the light of day for maybe 2-3 billion years. So we really are going someplace unique, never before seen. So a lot of the basic questions we understand about the moon, like what's the dirt made out of, we're asking again, is it made the same here at the poles where things could be very different? So we want to ask these questions. So we're really going to look at, this is the primary objective, what is that hydrogen that we see? But also, what's the regolith, the moon dirt made of? What's its strength, its depth, its grain size, composition? Is it even similar to the Apollo sites? And that'll help us decide whether or not we need to do follow-on missions there to explore it some more. And one of the aspects that I'm very interested in is the lunar atmosphere. Usually you hear there is no atmosphere, and you could argue it's an exosphere, not an atmosphere. But there is, and there are volatile processes that occur on the moon. And it's these volatile processes that are potentially responsible for that hydrogen. So we're very interested in how that lunar atmosphere respond to our impact. You'll hear in a minute, how did the water get there? Well, it could have been from impacts from asteroids or comets. We're, in a sense, mimicking one of those impacts, so we get to study that process and understand it a little bit better. What are the timescales for it to recover? And then how do these volatiles, like water or dust, migrate around the moon? These are just basic, fundamental planetary questions that apply to any body without an atmosphere in the solar system, which are quite a few, and also have fundamental bearings on the delivery of volatiles to Earth in the inner solar system. So there's a lot of very exciting, interesting aspects to this mission. So some of you probably know this, but some of you might not, and I think it's really a kind of a cool characteristic of the lunar poles of the moon. How do you get a permanently shadowed crater? And that's how you actually get the water at the moon. So I phrase it here, how could you get water at the poles? Well, if you don't have an atmosphere, it volatiles, it evaporates off or sublimes off very quickly. Well, in some of these dark craters, this is an image of the South Pole of the moon from Clementine. You have these craters that are very, right near the pole. The South Pole actually is right about where this red dot is, on Shackleton crater. This is Shackleton. And the sun is very low on the horizon at the poles all the time. And the moon doesn't have a lot of tilt to it, so the sun never gets above the horizon by more than a degree or two. So in this little cartoon here, you can see that the sun may never actually get to the bottom of this crater, even as it goes around in a circle around this crater. And first test of a video here, we'll see if it works. An excellent example of this is this beautiful animation made from new Selene data, Kaguya data from Japanese satellite, showing the altimetry of the moon and then a model to represent the lighting. And you can pick a particular spot on the moon, like for example inside this crater here, right where I'm pointing, and you can see the black represents shadow. There are parts within these craters that no matter where the sun is during a lunar day, you never get sunshine down there. And without an atmosphere to transfer heat from one place to another, if you don't have sunshine, you get cold. So in one of these really dark craters that never get sunshine, you can get exceedingly cold. You can get down to minus 200 degrees below 0 centigrade. The permanently shadowed craters on the moon are among the coldest places in the entire solar system, which is a kind of a fascinating fact. So LCROSS will be the first thing to land hard in one of these permanently shadowed craters and bring the material up into sunlight so we can study it. And that's the only way we can study it without much more extensive capabilities. So why do we want to do this from an exploration standpoint? Water is expensive to haul to the moon. So if I'm interested in bringing water to the moon, something about this big, depends on how you do the math, it's going to cost you about $50,000 at a minimum probably. So I've drank about $25,000 worth of water here. Now, talking with some of the guys in Houston who are in charge of the astronauts, one of them in particular told me there's no way, in a great Houston drawl, there's no way I'm going to have my astronauts drink moon water. I'm not going to have them suck the water out of the dirt. We're going to bring the water. But, he said, we're really interested in not bringing our fuel to return home, or our fuel to go to Mars, or our fuel to go to somewhere else. Every time we launch the shuttle, it's a couple million pounds of hydrogen and oxygen. That's a lot of fuel if you want to bring it to the moon. So we're very interested in extracting hydrogen and oxygen from the moon, the basic parts of water, and using that to actually make rocket fuel. Actually doing this on the moon, too, proves to us that we can do it on Mars, which is one of the fundamental mission architectures for a human venture to Mars, is to in situ produce your fuel for the return home. Much rather try that first when you're 2.5 days away from Earth than 2 years away from Earth. So what this plot shows is how the poles could help you. There's hydrogen and oxygen all over the moon. It's locked up in the minerals of the dirt at various concentrations. And at the equator, for example, there's about 100 parts per million of hydrogen in the lunar dirt. And you can extract that by heating it up and driving off the hydrogen. At the pole, if there was 1% water ice, we think there's about 1% water ice in some of these permanently shadowed craters. That would explain the hydrogen we see. This is the energy in kilowatts per kilogram. So how much heat you got to put in to get the hydrogen out. To get it out of the dirt, you got to get it real hot. You need about 2,200 kilowatt hours to get the dirt out. Whereas if it's water ice, you know how easy it is to boil water or melt ice and extract hydrogen from it. So while it might be easier to go to the equator and dig up dirt as opposed to going to a minus 200 degree shadowed crater to dig up dirt, when you actually work out the cost production ratios, it's easily 5 to 10 times more efficient to dig up ice out of the poles than it is to extract dirt. Those are some estimates, some studies. So the fundamental position or going in, or our question we want to answer is, hey, do we really have this kind of ice at the poles? Is it worth exploring this further? Or should we just say, no, we're going to settle on going to the equator or sticking to Apollo-like landing sites in the future? So we're really interested in understanding the water at the poles for what's called in situ resource utilization. It's a buzzword you'll hear a lot. And if it's above 1% or so, then it makes polar mining very efficient. So that's the exploration side of the equation here. That's why the ESMD, the Exploration Systems Mission Directorate, commissioned the LCROSS mission. So what do we know about the polar hydrogen? Here's some pretty colorful figures of the South Pole. Here's some craters. If you remember, I was pointing to that Shackleton crater, that dark little crater with the pole right there. This is it. What's shown here is the white areas are calculated shadowed regions. So these are these permanently shadowed regions, clearly shadowed like snow. And the colors show where we see the hydrogen maps, or the hydrogen from the Lunar Prospector mission. The Lunar Prospector instrument had a very big footprint, had a very big view. So we're not exactly sure where the hydrogen is. It's about 70 kilometers or so across, depending on its altitude at any particular time. So you can see the distribution of blue. This blue means high hydrogen concentrations. Is kind of just smeared everywhere. So we really don't know where, if it's here or where. The theory is, if it's indeed volatile and associated with cold places, it's stuck in these cold traps. These cold, permanently shadowed regions are trapping this volatile. So a number of experts have deconvolved the data. They say, okay, if it's actually inside these cold traps, we can do some very clever processing techniques and kind of stuff it back in. And it's oversimplifying a very complicated process. But when you do that, here's a map that Rick Elphick, who is also at NASA Ames, generated, that's showing the percent water equivalent hydrogen, percent of water in these permanently shadowed regions. So here's Shackleton, it's about 0.5%. Here's Faustini, a little bit less than 0.5%, and so on. So these are kind of the water percentages we're interested in. You can see just from this map, though, still, we don't have the resolution or the understanding to understand what's going on within this crater. This is a pretty big crater. This is about 35 kilometers across. It's big. So where in that crater is the hydrogen? Is it everywhere in that crater, smooth? Why is this crater so much wetter, if it is indeed water, than this crater and that crater? Why is this so high? These are fundamental questions about that indicate something about the process or the retention or the history of these regions that we just don't understand at this point. So there's a fundamental question that we have to address is it uniform or heterogeneous from one crater to another, and how is it at smaller scales? It obviously differs on these big scales from 50 to 100 kilometers, but what about different at smaller scales? This is really critical, and this is what I'm going to get into in the next few slides. So at these smaller scales, what we're really interested in is it smooth? So is it evenly distributed at low concentration? So you can imagine that this auditorium is a crater. And you measured from space, on average, across the auditorium, 1% water. Now, you could create that measurement in a couple different ways. One, you have 1% water evenly distributed across the entire auditorium, just a frost, real thin frost. Or you could have a glass of ice cubes right in the middle or in the corner. And if all you see is, your view is just the auditorium, you can have a high concentration look exactly the same as a very uniform field. That's the problem. There are fundamental processes that are affecting those two possible solutions and members. So I call these low concentrations, nice and uniform everywhere, the smooth approach, or smooth representation. Poorly, and somehow within the project, we got to start talking about peanut butter. That's the smooth peanut butter. I don't know how, but then it stuck. There's another peanut butter pun, but I didn't mean that, actually. So the other end member is the chunky. They're just patches of ice. Originally it was, I think, said raisins and pudding to me, and then we got into peanut butter. We were hungry that day or something. But The chunky is that, yeah, there's a big block of ice over here, and everywhere else it's dry. That would make the same measurement that we've seen from Lunar Prospector. So that, of course, is the chunky peanut butter. That's really what LCROSS is all about. One of the things. First, is it water? That's a fundamental question we have to answer. And then, is it smooth or chunky? And that's critical to understanding about its science, from a scientific standpoint, the processes, the distribution, how it came to be, but also about mining. Do I have to go find the one ice block in the middle of this 20-kilometer crater? Or do I just get to scoop it up just about anywhere I like to go? That's really important. So craters, they're important. They're important across the solar system. You should all have great respect for craters. They are the dominant surfacing erosional process across the solar system. They occur today, and they're very important to the question that I just brought up. A point I like to make always is that there are about 2 to 3 LCROSS-sized impacts occurring on the moon now per month, and we observe them by impact flashes. You can observe them with a 10-inch telescope and high-speed video pretty easily. So the unique thing about LCROSS is we know exactly where and when this impact's going to occur. The impact crater that LCROSS is going to make is about 20 to 30 meters, so it's about the size of East Crater. This is the Apollo 11 landing site. Here's the landing module here. This is East Crater. They flew right over this on their way to here. This is about a 10-meter or so crater. These are important craters in the scheme of things when it comes down to hydrogen because of their excavation depth. An important thing to know about the Lunar Prospector hydrogen measurements is they could only penetrate the sense to about a meter, about 70 centimeters or 100 centimeters or so into the lunar dirt. So they are really only seeing the top meter of lunar dirt. So we know the hydrogen concentrations in the top meter, and we don't know what's going on below that. These craters, a 10-meter crater like this guy, excavates, rule of thumb, about a meter deep. So these kinds of craters are affecting what we see from Lunar Prospector, and that's very, very important. This just goes to show, this shows kind of the distribution of these. This is a 30-meter crater here, the distribution of these craters. So there's so many of these size craters per area on the moon. And this is important to determining whether or not you have smooth or chunky peanut butter, water. Here's a little schematic I've drawn of depth. So this is the depth into the dirt, and this is some kind of horizontal distance across the lunar surface. So you have these craters with 5-meter diameters that excavate to about a half a meter deep. The rule of thumb is, if you really want to know, crater depth is about 1/10 its diameter. These happen about every 1 million years per square kilometer. So if I stood around on the moon for 1 million years, within a kilometer of me, or so, you would see an impact that would create a 5-meter crater. A 10-meter crater, which excavates down to about a meter deep, the depth at which we sensed with Lunar Prospector, happens about every 15 million years. That's a pretty long time, actually, and the kinds of processes we think that bring the hydrogen, if it's water, into equilibrium, mainly diffusion and thermal gradients and things like that, have shorter time scales than this. So between these craters, we think things should be uniform. So when this crater hits, however, this impact hits and makes this crater, it disrupts everything. It throws out ejecta, it buries some, it excavates some, it heats up, it sublimes some water, some of that escapes, and it makes a mess of things. So you can actually kind of quantify exactly how disrupted that top meter should be. If you had a perfectly uniform frost, how disrupted it should be. And when you do the math for a 10-meter crater, it's rather simple math here. Crater diameter squared divided by the crater spacing, meaning the distance between a 10-meter crater, which is about 100 meters or so on the moon. And you get about 99% is undisrupted. So that's quite a large number. That means if the peanut butter is smooth, 99% of the area should have about a 1% water content, because that's what the hydrogen measurement is. So that predicts a smooth peanut butter or water. Now, if it's chunky, you had this one large cometary impact, for example, which happened much less frequently than asteroid impacts, but it delivered a big chunk of ice, or a large concentration of ice, that enough to result in the observations Lunar Prospector made, then it may never get disrupted in the last billion years, because you need just the right kind of impacts to disrupt it and distribute it evenly, and so on and so forth. So the two end members are testable in this scenario. If LCROSS hits and sees nothing at its detection level, and its detection level is below 0.5% water, then we would say, well, we don't have evenly, chances are really good, better than 99%, that we don't have uniform water everywhere. It is actually heterogeneous, and that's really important. So we've immediately confirmed or favored one model over another, and then we can think ahead about what we do next. If we do see water at the 0.5% or better, then that says actually it is uniform. So we aren't talking about chunks of ice everywhere, we're talking about a uniform smooth layer. If we actually get lucky and hit a chunk of ice, and we see 5% water, 2%, 3% water, then that says, yeah, that's the same as not seeing water. It is heterogeneously distributed. So that's key. That's one of the principal results or contributions LCROSS will make. And that will hopefully settle some of the debate we've had for the last 10 years over what is producing this hydrogen signal. So a little bit now about the LCROSS mission. The LCROSS mission is really a mission of opportunity. It's one of the several times I've been impressed with NASA wisdom, one of a few times. And there are a few. LRO needed a larger launch vehicle. It was going to go on a Delta II, and its mass grew, and so they needed a larger launch vehicle. Unfortunately, there's no Delta II Plus, and so they had to go to an Atlas. An Atlas carries a lot more weight, a lot more mass to the moon. And so suddenly NASA had an extra 1,000 kilograms of lift capacity to the moon with LRO. LRO had already been working on their project for 2 years at this point, but NASA said, let's go and see what people can do. So they put out a call to all the centers and said, what can you guys think of? And at NASA Ames, we formed a quick group called Blue Ice and really looked at this. We submitted 6 proposals out of Ames. 19 total were submitted to NASA, down selected to 4, and we were finally selected. All that occurred in a span of about 4 or 5 months, and because we knew we had to hurry. And oh, by the way, you only have $80 million to do it. So our budget is actually $79 million, and you had to get it done in about 2.5 years. So that's how LCROSS was born. Was you have 1,000 kilograms to the moon? What can you do with it? There were orbiters, there were several other impactor ideas, and so on and so forth. The unique thing about LCROSS that tipped the scale for us, and there's 2 things actually. One is we didn't use that 1,000 kilogram extra allotment for our impactor. We use that for what we call the shepherding spacecraft. This little bit here that you see on the end. I'll describe that a little more in a minute. What we used as our impactor was the space junk that they would otherwise throw away. This 2,300 kilogram Centaur booster that pushes ourselves and LRO to the moon. So in a way, we cheated. We got 3,000 or more than 3,000 kilograms out of the deal for the cost of 1,000 kilograms. And we also got then a very unique observing position. We got the best seats in the house for observing the impact. And that's how we're very different from deep impact. Our mission is frequently compared to deep impact, and actually a lot of our science team members are deep impact science team members. But deep impact was never closer than 1,000 kilometers from the impact. We're never farther than 600 kilometers from the impact, and we actually fly through the ejecta plume before becoming an impact ourselves. So there's essentially 4 stages, and I can show a movie on this real quick, for the LCROSS mission. There's the launch, where we launch stacked, LRO, the Lunar Reconnaissance Orbiter's on top of us, we're underneath, and then here's the big Centaur motor that pushes us to the moon. LRO detaches, goes on its way to the moon, starts its commissioning and mapping phases, and then we go on a 3 to 4 month cruise around the Earth. Around, it doesn't say, it got cut off Earth. And this is it's really hard to see here. Here's the ecliptic plane. We do a swing by the moon and get into a highly ecliptic orbit around the Earth, very large, 700,000 kilometers at times. And we do that to get positioned to impact either pole of the moon. So we get into an orbit that times things just right, so the moon comes around and we run into it. And we can go swing by the south or swing by the north, depending on which pole we want to hit. A very clever way to do this at very low fuel costs. So we do that for 3 to 4 months. We have a few calibration events in there and so on and so forth, but it's pretty boring. Then it all comes down to the last 9 hours. At 9 hours from the moon, we separate from the Centaur. We target it on its way. We separate this part of the spacecraft from the Centaur. The instruments turn and look at it as it heads into the moon. And then we generate a 4-minute separation between us, meaning we're 4 minutes behind the Centaur going in. It impacts. We take 4 minutes worth of data. We're actually on for an hour, but there's 4 minutes of useful, real critical data, and then we impact ourselves. So I can show a movie, but I don't think it adds much more to what I just described. Prospecting with 6.5 billion joules. That's what the LCROSS impact is, and that's what makes it unique, is we have relatively slow speeds hitting the moon compared to deep impact. Deep impact had a closing speed that was in excess of 10 kilometers a second into Temple 1. We have much slower impact velocities because we're just going to the moon. It's about 2.5 kilometers per second, but we have a lot more mass. We're at, like I mentioned, we have about 2,300 kilograms worth of mass. So when you do the math, that works out to over 6.5 billion joules of energy. Now, it's all about the impact. Very early on, we had a large team of varying impact specialists. They all have their opinions and their different methods for calculating what to see. But that was what we would see, but that was critical. So we did a lot of very sophisticated analytical modeling. This is called smooth particle hydrodynamic modeling, where they actually simulate each grain of dirt. We had some running on supercomputers with over 11 million grains of particles of dirt that are a few centimeters in size, and the simulations last all about 5 seconds, meaning we can only simulate the first 5 seconds of the impact. That's essentially the crater formation time, and then we do different code to calculate the ballistic trajectories out from that. We also do really cool gunshots at Ames using the vertical gun. There's a large vertical gun that is actually Apollo vintage that has been maintained, and I'll show a neat video. Pete Schultz, who many of you probably have heard of, has been using this gun for years and years to actually study impacts, and he's one of our team members, and this shows an impact from looking above in the vertical gun the way LCROSS will see it. So what we did is we simulated the permanently shadowed crater rim, the impact angle of about 60 degrees, which is our impact angle. It's going to be better than 65 from the horizontal, and the position of the spacecraft. So the sun's coming in from the side. I'll play that again. What you see is the flash, that first area right there. You saw the flash. We'll see that. You see a high velocity vapor plume come up the middle. That's very unique to a low velocity impact. Some real new impact science Pete's been doing. And then you see the ejecta start to come out. We call that the sunrise. So you can't see the crater floor. You can just kind of maybe see it. And that's actually light from scattered light coming off the particles. And then the ejecta continues to come out in a spectacular way for several minutes in the real world, the last several minutes. So we've done all kinds of work to try to understand this impact. And again, this impact is going to be quite unique. How is it different from other lunar impacts? Some of you may know that we've impacted the moon quite a bit. Our first missions to the moon were just hit the moon, as the Ranger missions, and we finally got it right, I think, on Ranger 4. We finally hit it. We've also impacted it much more recently. Lunar Prospector, that mission that discovered the hydrogen, You run out of fuel and you're in orbit around the moon, there's only one place you're going to end up, it's the moon. So Lunar Prospector actually said, well, let's try to actually do an experiment. The same kind of experiment we're talking about with LCROSS. They impacted inside of Shoemaker Crater, one of these permanently shattered craters, but it was a very small spacecraft, about 150 kilograms, and it came in, because it was in a low orbit around the moon, comes in at a grazing angle, very low angle. What this diagram here shows is a total mass of ejecta, the stuff coming up as a function of the impact angle for a couple different impacts. So here's Lunar Prospector, way down here is this little dot. Because it's coming in at this grazing angle and is such low mass, it hardly would have thrown up any mass at all. Nothing was seen. A few telescopes tried to observe it from the ground on Earth, but nothing was seen. Now, SMART 1, which impacted almost a year and a half ago, I think, now, was a European mission to the moon. It was a technology demonstration mission. It too ran out of fuel, and they brought it in about 23 degrees south of the equator, not at the poles. But it was comparable to Lunar Prospector. It was a couple hundred, about 240 kilograms, so a little bit heavier, but it was also coming in at a grazing angle. It was coming in at like 3 or 4 degrees. They're actually worried they're going to clip a mountain, and that's actually what we think they did. They clipped a mountain and before hitting the surface. So there were predictions. We made predictions with them, and we actually had observatories in Hawaii observing it, practicing for LCROSS. It could either be down here, or if it hit a hillside impact, our models predicted it could be around here. The Canadian-French Hawaii telescope actually did observe the flash, and they did observe ejecta dust being lifted up into sunlight, and there are papers coming out on that soon. So this was proof of concept that with the new telescopes that have been commissioned in the last 10 years or so with very fantastic detectors, you can even see a very small impact like this. Not just the flash of the impact, but actually the dust coming up and being illuminated by sunlight. Now, LCROSS is way up here. It's, again, we come in at a very steep angle, and we have 2,300 kilograms, so we're throwing up a lot more mass. Our shepherding spacecraft, when it impacts, it's about 700, 720 kilograms. It starts out near 1,000, but it burns a lot of fuel just getting to the moon. So we'll actually have two very respectable ejecta clouds. You saw the impact video from looking above. That's how we'll see it on our shepherding spacecraft. But from the side, it'll look like this. This actually shows the height above this. This is the South Pole, so that's why it's going down. This shows the height in kilometers. So that's 1,740, 1,760, so it's a radius. So this height right here represents about 20 kilometers above the lunar surface. What this shows is a density of particles, and I didn't put the scale on here on purpose. It'd be just too confusing. But the point I want to make is that most of the ejecta is going to be constrained in the lowest 5 or 10 kilometers above the surface. Some material does get very high. It's got high velocity component to it. Not as much as deep impact would, for example, because we're a slower impact, but some. And at last, this is 95 seconds later, our predictions say that this ejecta will finally fall out and settle out in about 3 minutes' time. But you can actually, I'll comment about how bright that is from Earth. It should be bright enough to observe with a 10 or 12-inch telescope on a clear night. So where are we impacting? This has been very difficult. You know, hey, it's a crater. You find a crater, you impact. Well, it's hard because we don't dictate when we launch. LRO does. So we have to be prepared for any possible launch that they have on their books. That said, we want to also make sure that there's a ground-based component that can observe the impact. So it has to impact at a certain time and place. We need to impact such that there's the maximum amount of sunlight above the crater so that the ejecta comes up. The sooner it sees sunlight, the sooner we get information. So we have to consider that. We have to also consider the target properties. So we're trying to make an impact and have ejecta thrown up into sunlight. It's not good if you hit a slope this way because the ejecta goes out sideways. And likewise, we want to hit something nice, fluffy, like flour, as opposed to gravel or rocks. Gravel, if we impact into gravel or rocks, our energy, that 6.5 billion joules, goes into crunching rocks rather than throwing it up into space. And you can do this experiment at home with your kids. Get a sack of flour, pour some in a pot, get a sack of beans, pour that in a pot, have your kids hit it and see which makes a bigger mess. And it's exactly the same thing we're worried about here. We want the bigger mess. We want the flour to go up. So we have to consider all these things. And as I mentioned, the LCROSS crater is only going to be about 20 or 30 meters across. So we're worrying at a scale that we have very little data on for the moon. LRO will finally provide this data. Actually, the Japanese mission is providing this data now, and the PI for the terrain camera is actually coming out to Ames in a few weeks to visit with me to talk about this sort of thing. So we only now finally have the kind of data we need to really understand where we're going. The problem is, of course, we're going into a dark crater, so you can't see down there. So imaging doesn't really help you. The Japanese have demonstrated that you can actually, by adding a bunch of images together, see the bottom of these shadowed craters thanks to light that's just reflecting and scattering off of the walls of the crater. So we really have the technology now and the missions and the data now to actually support this mission in a proper way. And of course, there has to be some hint of hydrogen there too. So when you throw all these things together, you're actually you run out of actually sites that you can impact. So this is a North Pole. These are candidate North Pole craters. We examined several just to get a flavor. We have a targeting accuracy of about 1 kilometer. So we'll be able to hit to within 1 kilometer, 3 sigma. The navigation team wouldn't let me take advantage of that full capability. They started to sweat too much when I started showing them smaller and smaller craters. So we have a rule that I can target a 3.5 kilometer area. And so the craters we're looking at now for our April launch dates are this region, this, again, white area here represents shadowed regions, permanently shadowed regions within this crater. This is a radar data set, by the way, made from the Earth. So actually we can illuminate parts of these permanently shadowed craters with radar. Very helpful. And so we're looking at crater A and crater F. A lot of these other craters, either the illumination isn't good or the surface isn't good. For example, crater C was thrown out thanks to the Japanese data that showed that slopes were just too steep, so we're avoiding it. E is on the far side, so this is the far side of the moon from here down. Can't see it from Earth. So when you kind of throw all this together, you end up with this little slice, just a couple craters that you really want to focus in on. So those are the craters we're planning on going to for our upcoming launch. The spacecraft and payload. As I mentioned at the beginning, the whole project is an experiment within NASA. Can you build to a fixed price, which is not normally how NASA does missions. Usually there's a cost bogey, there's a cap you build to, but then as requirements change, you can go over it. We were told by the Exploration Mission Directorate, you go over your $79 million and you're dead. We mean it. And so that plus, we only had 2.5 years to put this all together, said that we had to do something innovative compared to how we normally would do missions. And what we came up with, along with our primary contractor, Northrop Grumman, is capability-driven products, meaning rather than me, the scientist, and the science team saying, we need to do A, B, and C. Let's go do that. Those are requirements, and we'll negotiate a little, but we got to meet those. That's how a typical NASA mission is frequently done, and what that does is it drives very unique systems, very expensive systems, very lengthy development schedules. What we did is we started from the bottom up and said, what capabilities exist? We did this on the spacecraft side, we did this on the payload side. So for example, on the spacecraft, we couldn't say, we're going to build a new spacecraft. What exists out there that we can take advantage of? One was LRO. LRO had been at this 2 years. So we said, can we have your avionics, your spare avionics, or build a set just like it? And yeah, that's a good idea. Let's do that. Okay, that'll save us development time. Then we looked around and we said, Northrop Grumman came up with this really brilliant idea. What can we build the spacecraft out of? You're putting something between the rocket booster and LRO. LRO is going to be pretty dissatisfied if you put a cheap something in between them, right? And an unproven something. And proving something costs money. So they had the idea of going with this giant piece of yellow sewer pipe. This is called the ESPA ring. It's an acronym in an acronym, so I won't go into what ESPA stands for. But it's an adapter ring that was designed specifically to bring secondary payloads on Atlas missions. So it has already been designed and tested and qualified to stick between the primary payload and the motor. It's a giant chunk of aluminum. It's about 150 kilograms. You know, there's no worries. You can complain about it, but no one would take you seriously. That made LRO very satisfied that they essentially were mounting straight to something that was meant to be mounted to, and all they had to worry about was the peripheral. And the peripheral, we could demonstrate, was very robust. It also saved us a lot of money. It was built. So this piece of sewer pipe has these little ports on it. Normally, you put a little small spacecraft on each of these ports, little secondary missions. What Northrop Grumman came up with that is really genius again, that made this possible was they use each of those ports as a little panel, a little module that contained various spacecraft parts. The batteries are over here, the computers over here, the navigation systems over here with the star tracker, and so on and so forth. And over here is the payload. This is a large solar panel. So it's modular. All these things actually just come on and off and so on and so forth. And very accessible. The tank in the middle, that's a fuel tank. That's a leftover tank from a satellite, series of satellites called the TDRS satellites that was left over. It was in a warehouse. We got it, changed the plumbing a little bit, went with it. The rule, the kind of philosophical overpinning was, or underpinning was, glue it. Don't develop it. Find things that all you got to do is glue them together. And that's what we did. What it also allowed was this payload panel to come up to NASA Ames. NASA Ames developed and integrated and tested the entire payload. We went down to Northrop Grumman, got the panel, brought it up to Ames, integrated everything on it, drove it back down there in a FedEx truck, white glove service, and stuck it on the spacecraft, plugged it in. And that's how, you know, it had to be to make these things work out. This is a spacecraft going into a thermal vacuum chamber. This is a very large chamber that simulates the space environment at Northrop Grumman. This was in June of last year. So we were ready. Our original launch date was October 28th through the 31st of last year. We were ready actually to be strapped on and go at that launch date. So we met the schedule both under budget and with schedule slack across the board. So this is the payload developed here at Ames. It's in what we call the pod, the payload observation deck. It's this large aluminum housing that acts as an optical bench. Everything's mounted to a single piece of aluminum. So if you align that one piece of aluminum, you know how everything else is aligned. And it's got a lot of instruments in it. And that's actually what's kind of exciting is for this very inexpensive mission, we have 9 instruments on board. And again, we use the philosophy of looking at what capabilities existed. Rather than say, we need an instrument that does this, this, and this, and this, we said, well, these are the things we're interested in. What exists that can accomplish those things? And for example, our near-infrared spectrometers, which is this telescope here, it's really one of the workhorses for looking for water for us. This instrument was developed by a company on the East Coast, the spectrometer was, called Polychromics. The instrument is used in assembly lines for measuring alcohol content in beer. It's really actually used quite heavily now for recycling carpet. And so it's rugged because they have it on their belt and they actually go up and measure carpet and so on. We essentially talked with them and said, your instrument measures the kinds of things we're interested in. It's built. Will you work with us to rapidly prototype a flight rugged one? We'll work with you to make it able to go in space. And that's what we did. The instrument providers delivered their instruments from requirements, from the contract signature, to when they delivered their flight units in 9 months. I mean, incredibly fast and way under budget. So really exciting. We have ultraviolet spectrometers. We've got a visible camera, near-infrared cameras, mid-infrared cameras, and a flash photometer, special radiometer for looking at the flash. So I'm going to play a little video here. Where am I on time? Running along. About done. But if I don't show the videos, it's not worth it. This is actually what we'll see from about 40 minutes out. Starts about 40 minutes out from our visible camera. That's about the field of view and aspect ratio of our visible camera. It's called a context camera. That little yellow circle is the field of view of our near-infrared and visible spectrometers. And this is us flying into the moon. It's not at real speed. From the time it starts to impact is 40 minutes. But what you can see is it's going to be a heck of a ride. We will be streaming the video from the cameras real time via the net. And so this is another aspect of the mission that I was really keen on making happen, was making this a real-time event to experience, for everyone to experience with us. I was so impressed with Deep Impact. Ground observers saw the impact before NASA saw the impact on Deep Impact. And that's really important for generating the excitement, the interest. Also, I am now on a couple Apollo hoax websites as someone who's propagating the hoax. I think it'll be hard if we stream the video and can see the impact simultaneously for us to, really pull that off. So in a hoax-like fashion. So hopefully this will convince everybody that it really happened. Seeing the video, at the same time you see the flash up in the heavens. So we've got a few cameras. This is the visible camera, but we've got 5 cameras in total, and this is me and the various colors of the cameras. Here's the visible camera, and they're rotated in different ways because of the way they're rotated in that pod. And me in the near-infrared wavelengths and in the thermal wavelengths. All these will contribute information about the impact event from the beginning to the end. And even seeing the crater we made. We think we will be able to see the crater we actually generated in the infrared in the very last seconds of our mission. An interesting aspect about these 2 images, we have filters on the 2 cameras so that they enhance water features. Near-infrared will enhance ice features, water ice, and mid-infrared will enhance water vapor features. You can see the difference in my skin tone and hair, and that is attributed to differences in actually the water and chemical and the reflected properties of my skin. So you can see by differencing these 2 images, you can actually learn about the distribution of the composition of whatever it is you're looking at. And that's one of the principal purposes of those cameras. So ground-based observations, I'll just wrap it up with this. Again, they're equally important to the space-based observations are the ground and orbiting observations. It's part of the robustness of the mission. So we go to great lengths to make sure the impact occurs over Hawaii at a good time. And this shows the impact geometry for Hawaii for the April 25th launch. Here's the west coast of the United States. This circle shows a 45-degree elevation angle to the moon, which is a requirement. So we're right at the edge of it here for Hawaii. It's going to be low on the horizon for us on the west coast, but should still be quite observable, hopefully with good weather, not like tonight. And we essentially had to do this for every single possible launch date that LRO presented us. We had a selection of a number of astronomers that are being funded directly to help us do these observations. And we had the first telecon with the entire team today. And these are the folks who are planning and are supporting the observations all the way down from the Hubble Space Telescope. We have 5 orbits from Hubble will be observing it. Odin, which is a space-based platform, European space platform, will be observing it. And then a number of assets, most of which are in Hawaii, but some in New Mexico, some in Arizona, and also even in Korea. So we also have interest from other European colleagues who want to observe it. The impact lasts 4 minutes, but the effect on the atmosphere could last hours to days. And we have the right kind of instruments now to really detect these kinds of things. So there's a large part of the community that's interested in monitoring the event as it occurs and then following the impact for several hours to a day or 2. For those of you who are astronomers, this is the apparent predicted magnitude or predicted apparent magnitude at time after impact. And you can see it lasts a minute and a half or so. It really starts to dim out as the ejecta gets more and more faint. The height of the cloud that this kind of brightness represents as an average is about 10 arc seconds or so, so it's fairly large and is fairly bright. So we really think that this should be, with a good telescope and a clear night, observable from the ground by just about anyone. Don't need a professional to observe it. So, last slide. Thank you for your patience. We'll talk hopefully in 7 months with some really exciting results. Definitely going to be observable, so if you're keen on that, there is a large amateur astronomy group that Brian Day is heading up to support us. The amateurs are supporting us now. I didn't talk about it, but there's an incredible process of actually pointing a 3.5 or a 10 meter. We have the Keck telescope, a 10 meter class telescope looking at this. How do you point that at the moon? They hate the moon, you know, and now they're asked to point at it. Dan Wooden at Ames, who is a deep impact member and is our chief astronomer. There goes my battery. Good timing, huh? Developed over the last 6 months with a lot of hours on IRTF, the procedures for observing actually these events. And using guide craters rather than guide stars. Normally you use a star to hold your pointing on an object. They've developed a whole routine for using guide craters on the moon to point at a particular spot on the moon. And they've demonstrated half arc second repeatability. That's pointing to the moon, a 10 meter, well, theirs was a 3.5 or 2 meter telescope to about 500 meters or a kilometer or so. Incredible. And they've been using amateur observations of the moon, hardly amateur. Some of these images are just spectacular because we need to get looks at the moon at all different illuminations and angles so that they can understand for any given launch date what the guide craters are. So it's actually been a really good, productive relationship with a lot of astronomers in the amateur community for this project. And I'll leave it with that. Thanks. And I hope you don't have questions about the slides.
Okay, we do have time for questions. Thank you very much for an illuminating talk. We are going to ask people, if you have questions, to line up at the 2 microphones in the middle of the auditorium. Please do try to keep your questions brief so everyone has a chance to participate. And I'm going to ask Dr. Colaprete to take questions one at a time.
Can the chemistry of, any planet, be it Moon or Mars, can it be manipulated to eventually, be able to sustain life there?
Terraforming, be hard to terraform the moon. It's a small body, doesn't retain much of an atmosphere. Mars, there are lots of speculation or thoughts on that matter. And there's a colleague at Ames, Chris McKay, who's a very strong proponent of terraforming Mars. I think it's something that is grandiose, and I'm more worried right now about just getting LCROSS off the ground. So it's an interesting discussion point. I actually haven't given it much thought.
Let's do one question per person.
Yeah, okay, yeah. And I can stick around if you have a few more questions afterwards. Yeah, over here.
Okay. You mentioned that this impact vehicle has 5 cameras going in to record what happens going in, but it seems like you're most interested in recording what happens within the 4 minutes after the impact. Do these cameras have any usefulness after the impact? Are they gone? And if they're gone, what is your primary source of information for those 4 minutes?
The cameras are on the shepherding spacecraft, the following spacecraft. So that Centaur, the ascendant stage of the rocket, is our primary impact. It impacts, we're 4 minutes behind it, so the ejecta cloud's coming up. We're flying at that ejecta cloud with our spacecraft, with all of our instruments going, beaming real time to Earth all of our data. We eventually fly through the ejecta cloud coming up. We have a side viewing spectrometer. It looks at the sun, watches the sun set behind the ejecta. And we monitor, then we get imaging of the impact in the ejecta cloud all the way down until we lose communication with our shepherding spacecraft, which will occur as we duck behind the crater rim ourselves, which is about 2 or 3 seconds before impact. We're moving at about 2.5 kilometers per second. So yeah, we get all the data from the shepherding spacecraft. I'm sorry if I wasn't clear on that, in that 4 minutes time. Then it impacts, and yeah, those cameras are then 6 feet down, and I don't think they'll survive. But all the ground-based observers will be able to see that second impact. And so we are very interested in, that could give us information on the distribution as well. Yeah, so hopefully that answers your question. Yeah, another one here?
Since all of this information and speculation is based on there being hydrogen in these areas, what are the other explanations of hydrogen in these areas, and what are the chances that it's actually water?
I didn't cover that. I should have mentioned it at least. It's an excellent question, and that actually explains why we have such a broad range of wavelengths of different data sets. Everything from the ultraviolet through the visible, through the near-infrared, through the thermal. It could be water. It could be hydrated minerals. Minerals that just clays, for example, that take up water, bind water in them, so it's not water ice, but it's water hydrogen bound in these minerals. It could be free protons. The sun is shedding protons in its solar wind all the time. These solar protons rattle around the lunar surface. Typically they escape, but in very cold regions, they can linger long enough that they get trapped, chemically bound to some of the minerals. So it could be free protons that we're seeing here. That's just hydrogen. It's not water. It's not anything. So that's really important. We can detect everything fairly easily, convincingly, except free hydrogen, because that you need like a mass spectrometer. So we rule out water, or rule in water, hydrated minerals, a number of hydrated minerals, even organics. It could be organic species. If the hydrogen is from cometary sources, which many think it is, it could be in the form, we know there are organics and comets. And that's the great thing about these permanently shrouded regions, is they could be these treasure troves, these time capsules of all kinds of gunk that's hit the moon, all kinds of volatiles. We think there's probably CO2 in there, SO2, methane could be trapped in there, it's so cold, water. All this could be, if it found its way and somehow got buried deep enough or diffused deep enough to be protected from cosmic rays and sputtering, then it should still be there. And we're going to go take a look for it.
Got a quick two-part question. First, what is the angle of the lunar surface as seen from the Earth at the time of the impact? And second, are there any planned spectroscopic measurements from telescopes on the Earth or orbiting telescopes that will complement the capabilities on your shepherding spacecraft?
Yeah, absolutely. Unfortunately, because of, again, we don't dictate our launch date, LRO does, we're impacting just after northern summer. So the moon's got this libration, this wobble back and forth relative to the sun and Earth. And so right at the time of our impact, it's about, I think it's a little under a degree. I'd have to check. But there's it is going to be pointed towards the Earth, and it's not going to be optimum. The optimum's a little bit earlier, like in June, but it will still be enough so that Earth-based astronomers can view it. That was a requirement and a really hard one to meet. We actually push back on LRO trying to get them to move their launch dates when we run into trouble. There are absolutely spectroscopic measurements being planned. There's a lot of imaging at different wavelengths, high-speed imaging. The NIRSPEC, for example, is a very high-resolution spectrometer at Keck in Hawaii, and it can see non-telluric, non-Earth water lines. The problem for looking for 1% water in a dust cloud on the moon when you're on Earth is you're surrounded by 10% water, even at 40,000 feet. There's just water everywhere. So you actually have to find special lines in the spectrum that are not of Earth origin. And there are some that can be viewed by these special instruments. And they think they can see to less than 1% from the ground. And so they'll be observing. HST, we're using a different approach. We image the moon with its ultraviolet camera to observe the impact and image the impact. And then we go to a spectrometer, a GRISM, to observe an emission line from the hydroxyl radical, OH. And it emits at 308 nanometers in the near ultraviolet. And it is a product of water photolysis. So this water, if there's water ice or water vapor in the plume and it starts to photolyze due to ultraviolet sunlight, we can see that emission line. So we'll actually watch for that on subsequent orbits as it goes on. So yeah, we are looking, there are other folks looking for water lines out past 3 microns and 4 microns and so on. So that's some of the hot non-telluric water lines I mentioned. The flash itself is interesting. The brightness of that flash is a function of volatile content. And so if we hit someplace with even just 1% water ice, it would be maybe a factor of 100 times fainter than if you hit just dry dirt. Unfortunately, there's other things that can cause it to be 100 times fainter too. So, like rocks. So that's why we're going to take all these data sets together and, you know, overlay them, so to speak, to really come up with a most convincing conclusion.
Hi, I'm Lou, and you mentioned that there are many scientists going to be observing as a team, and I was wondering if you could go into more details, such as if there's airplanes going to be going up to get out of the clouds, and where you personally are going to find a cloudless observation point.
Well, that's another reason why we have many observers all over the world, because if it's clouded out in Hawaii, we're going to be very disappointed, absolutely. Sophia should be just the airplane stationed out of Dryden Science out of Ames will be just commissioning its science instruments at about that time. So we're definitely working with Sophia to hopefully get some measurements, some observations with them and the instruments that will be on board. HST, hopefully no clouds for HST or Odin, which are very good. Speaking of spectroscopy, Odin looks way in the microwave for interstellar water. So it's like looking for, you know, molecules here and there in the interstellar space. So we're really thrilled. They just got a mission extension that we were hoping for, and they just got it. We just found out a couple weeks ago. So yeah, that's another part of the robustness we've tried to build into this, was not rely on one observatory in one place, not rely on one particular wavelength or color to look at. Really try to spread yourself around so you can take advantage. We had a lot of, you know, unfortunately the impact itself only lasts 4 minutes. So you had to pick some place where that was going to happen. Hawaii has the best instruments, in our opinion, for making these measurements. You know, God willing, it's a clear night. We've had luck. New Year's Day, we had an observation of the North Pole, and it was blizzarding up there. And so they you know, for the safety of actually the engineers, we said, don't drive up the mountain, open the dome, stay. So, yeah, that's a risk, and we appreciate that. But that's why we have measurements on our spacecraft. That's why we measurements on HST. There will be follow-on measurements by LRO. LRO has a hard time observing it. It's at a very low altitude over the moon when the impact occurs. And it's going to be zipping by pretty fast, and it's not designed to watch something quickly as it goes by. So they're doing a lot of pre-impact characterization of the site, and then they will try to see the impact, and then they'll do a lot of post-impact characterization. And some of their instruments, if, for example, we hit some water and it recondenses out onto the surface, they'll be able to see that at very small fractions, very small amounts. They'll also be able to see the atmosphere effects very well. So hopefully, you know, some of these assets will return enough information to answer the questions. Hopefully that answered your question. But the team is from all over the world right now, actually. Yeah, over here.
Hi, I wanted to thank you for your talk. And my question has to do with the impactor. So this is a oblong Centaur rocket booster.
Tin can.
Yeah. So like using your pot of flour analogy, if I were to throw a ballpoint pen at a flower, it could hit straight in.
Yep.
Or if I, you know, sent it spinning end over end, maybe I'd get a better impact. Do you have any control over that?
Yeah, and I showed I showed actually some of the smooth particle hydrodynamic code data. We modeled the tin can. Pete Schultz is just now doing some impact tests with hollow cans. And actually, if I had to pick an impact for this experiment, I'd pick a tin can. I wouldn't pick a deep impact impactor, which was a higher density copper slug, okay, 350 kilogram slug, but we only measure down to that meter. So if I had something that was higher density, more compact, it would penetrate to 5 meters, 6 meters deep, and actually the material that would get ejected into the atmosphere, into the sunlight, would be from deeper than a meter. A tin can, and this is a great experiment again to do with your flower, do exactly what you said. Get something hollow, like a tin can, make it a little heavier so it has a bigger impact, and then get a golf ball and throw those various objects at it. You will get very different impacts. The tin can pancakes. It's like a belly flop. So you actually only dig down a meter or two deep, and so you excavate, but you throw up about the same amount of material because it's the same energy. So what happens is you get a broader, wider area that's excavated more shallow, and that's exactly what we want. We want the 1 meter or 1.5 meter stuff. We don't want the 5 meter stuff. Regarding can we control it, we've done, as I mentioned, Centaur's never flown 120 days in space and then done their separation system. They've done a lot of qualification work for us to show that it will survive. There are 8 springs that go around that kick them off. All their studies and tests indicate that the wobble will be minimal, and we shouldn't teeter too much during that 9 hours flight in. We have actually, right after that separation, we turn around and we turn on some of our cameras in high speed mode to watch the Centaur float away from us, precisely to understand your concern. Did we get a tip-off? Are we going, and then can we expect an end-on hit or a dumbbell hit, as we call it? Most of the mass in the Centaur is at the front and back with a thin shell between. And so if it hits, like you said, downward like this, you get a very different impact. You actually will see in the the light from the flash, we'll see the 2 ends hit. We'll see the first and then the second on top of it. It will still pancake flat, though, because those are relatively low density. If it hits sidewards, essentially you get 2 different smaller impacts that are conjoined by this dumbbell bar between them. It does produce a different crater. So that's one reason why we actually want to really do a lot of good post-imaging analysis. We really think we can image the crater with LRO, and both in the radar and in the visible, by using the same trick that Selene has demonstrated, imaging scattering light, to actually see the crater. And that'll help us actually understand where that ejected material came from. Eventually, we're going to use code models to put the ejecta back in and understand the depth distribution of the hydrogen as best we can, or the depth of regolith that we saw as best we can from the impact. Hopefully that answers your question. It's a real effect, and we're trying to account for it as best we can. We don't have control over it, though. Once it goes, it's a free flyer.
All right, let's thank Dr. Colaprete.
Thank you again.
Dare I say your lecture was a hit? And we'd like to thank everyone for coming. We'll see you at the next Silicon Valley Astronomy Lecture. Drive carefully.